Hello everyone, myself Komal and my teammates Navya and Pavan. We are here to give presentation on the project titled connect-4 game which we have developed in AI. So in this presentation, we are going to see what is connect-4 game, game representation, winning model, winning strategy, task environment, state representation and how we implement the min-max algorithm in this project and finally the conclusion of this project. So, what is Connect 4? Connect 4 game is also called as zero sum game, which means one party wins the game or there will be a tie between both the players, but there cannot be any win or loss state for both the players. So, this is also called as zero sum game, and the game representation will be in the form of 7 columns and rows that are vertically and horizontally suspended to each other. So here the player take their turn in order to drop their tokens into the columns where the token will occupy the lowest available space in the particular column. So the main objective of this game is the first player or the second player who tries to place all the tokens in the vertical and horizontal or diagonal manner, then the player will be considered as the winner and the game will be in a winning state. So the main strategy in order to play this game is the players should try to block the opponent moves and they should create the opportunities for themselves to place their token in order to win the game. So coming to this mathematical model representation of this connect-4 game. So the mathematical 7 by 6 multi-dimensional array where x are the rows and y are the columns. The below are the winning states of the connect-4 game. We go through every state. If suppose we take the equation 1, if suppose x is 0 and y is 0, then the next state is x is 0 and y is 1, and the next state is x is 0 and y is 2, and further x is 0 and y is 3, which is represented as 0 0 0 1 0 2 0 3. When the 4 points are placed diagonally, this is considered as one of the winning state and it is also called as diagonally winning state. Similarly, we consider the equation 2. We can place the points vertically so that it is called as a vertical winning model. Similarly, if we consider the third equation, we get the horizontal points in the game. We consider it as the horizontal winning model. Now, if we look into the game representation, as we discussed in the first slide, this is the board where we will be used for the connect-4 game. So here we have 7 vertical columns named A, B, C, D, E, F, G and 6 rows 1, 2, 3, 4, 5, 6. So when the player 1 or player 2 take the chance, they place their own tokens into the one of the columns, then the token gets into the lowest available space of the particular column. If the player places into the column D, then least available space is D6 cell. So the token has gone into D6. Suppose if the player 2 takes the chance to place his token apart from the column D, if he tries to take any other column, the token will go and sit into the 6th row of these columns. If suppose he tries to place the token in the column D, then the lowest available space is D5. So the token goes and sits in the D5 space. In this way, the players will try to place all their tokens vertically or horizontally or diagonally in order to win the game. And further will be continued by Pavan.
As we have already seen the mathematical representation of the winning models, here is the pictorial representation of the horizontal winning model. This is the horizontal winning model. The player who has chosen yellow tokens which are placed horizontally are considered as a winner and game is in the winning state. Similarly, here is the vertical winning model. The player who has chosen red tokens, placed them vertically, is considered as winner and the game is in the winning state. We can see tokens connected together in the game. Similarly, we have diagonal winning model where the player placed 4 of his tokens diagonally. This can be either in the right diagonal or left inclined diagonal. This is called as the diagonal winning model. So we have seen all the winning models so far. Now we will move on to the winning strategies. So we have to follow 3 main strategies in order to win this game. The first strategy is place in the middle column. So if player 1 or player 2 who tries to play the token in the middle column, that is column D, then they will have high chances of winning because he will get the chance to place the token on the right, left, upwards, or both right and left diagonal. That is 5 different directions and have max chances of winning this game. Coming to winning strategy 2, making trap of the for the opponent. Suppose the player 1 has placed his token in column D, then player 2 should make a trap and place his token against the player 1. In order to block the player 1, so we have placed them to the adjacent sides to this token, and available adjacent sides are D5, C6 and E6 because the lowest available space are E6 and C6. Because in the beginning state, he is having only those are adjacent sides to block the opponent moves. So this is the second winning strategy of the connect-4 game. Now we are moving to third strategy. This strategy is that player should make 7 shape. When the player tries to make 7 shape by placing tokens either right or left, upside or downside of 7 shape, then he has more chances of placing his tokens in different directions. In this case, we can clearly see that he has multiple chances to place the token and win the game. So here you can see the task environment. The first one is fully or partially observable. Here the game is considered as the fully observable environment as it has access to the full board. And the second is single or multi-agent, 2 players to play the game. Third one is deterministic or stochastic. Game is considered as a deterministic because it can determine the next state of the game. Fourth one is episodic or sequential. There are no episodic in the game. The past actions define the current actions or next steps in the game. Static or dynamic. Time is not factor to making the moves in this game. Discrete or continuous. It is discrete environment because it has final number of states. Next will be carried by friend Navya.
State representation. The state representation for this game is the grid consists of 7 columns and 6 rows. The total cells in this game will be 42 and there will be 2 players, that is player 1 and player 2, until either of the player place the token in the grid that will be in the blank state, that is called blank B. So the total number of possible states available for this token is over 4 trillion. According to the number pile video which is published in 2013, S. Edelkamp and P. Kissman, they both have calculated the number of possible states for this connect-4 game. Here the possible states calculated given as over 4 trillion states. Out of the 4 trillion states, we have non-terminal states over 2 trillion which are considered as play on, which means keep playing the game. Coming to terminal states, we have nearly 2 trillion which are game over states, which is either you can win the game or else you can completely draw the game. This is all about the state representation of the connect-4 game. Here we are using min-max algorithm for implementing the connect-4 game in artificial intelligence. Here we are choosing the player 1, choosing maximizing the score, and player 2 choosing the minimizing the score, and we have to explore each possible move within the game tree. We should apply the recursive method to evaluate the states again and again in order to play the game. As we are involving the min-max algorithm, the time complexity of this algorithm is O of b power d, where b is nothing but total number of possible moves, d is nothing but the maximum number of turns until the game ends, that means the depth of the tree. So this is the initial phase of the game. When the player 1 wants to play the game, he has 7 possible ways to play the game. Either he can place his coin in the first column or second column and so on up to 7 columns. For every game, each player has 7 different states to play the game. Here we use heuristic min-max function. Why we use heuristic means if we do not use any heuristic functions, the algorithm will keep on searching until it reaches the maximum depth. So in order to make a single move, it takes more time. So to reduce that amount of time for education or to make move in shortest path possible time, we should use heuristic function. The heuristic function here is given by h equals to x4 into 1000 plus x3 into 100 plus x2 into 10 minus y4 into 1000 plus y3 into 100 plus y2 into 10. The player X represents the yellow player, the player Y represents the red player. X4 represents the 4 yellow coins in a row, X3 represents 3 yellow coins, X2 represents 2 yellow coins. If we substitute the values in the equation, you will get the heuristic values. Based on the heuristic values, if it is player 1 turn, it will choose the maximum. If it is player 2 turn, it will choose the minimum value. Out of that all heuristic values that are calculated, when you calculate board score, x4 and y4 both are zeros. We don't have 4 dots that are connected. Coming to x3, we have one diagonally. It is connected. So 1 into 100 equals to 100. We don't have any 2 dots that are connected for yellow. So that is 0. First whole equation is 100. Minus here we don't have any y4s and y3, so they are cancelled. Coming to y2, we have 2 dots connected in horizontal way and vertical way. So 2 into 10 is 20, that is 100 minus 20 equals to 80. The board score is calculated as 80. This is the pseudocode for implementing the heuristic min-max algorithm. Here we are doing the min-max algorithm along with the data pruning. Now we will give the presentation on the game by using Python code. Player 1 has chosen the red token, that is the human. Player 2 has chosen the yellow token, that is machine. As we discussed, the tokens are being placed in the lowest available space in each of the column. As we seen that the player AI won the game. So the execution of the Python code is successfully working. Coming to the conclusion of the game, the project utilizes a min-max algorithm for optimal move selection because the AI actually outperform the human player, because each time you play the game, most of the times the AI played well because it have the ability, and we gave the ability to think most possible number of states and telling it to choose the best possible states. But as a human, we cannot calculate all the possible states and we cannot remember all the states. But as a machine, it have the memory, it can calculate all and it can choose the best one. Hence it outperform human player. So coming to the next, tuning the number of depths in the min-max function can have a significant impact on the AI player performance, because with the lower depth potentially leading to worse results, because if we don't have maximum depth or best depth, the AI player can choose or calculate only less number of states. It has to choose only from that states. If it calculates more possible states, it can choose that the best one. Then this agent will have more performance than the one which have the lower depths. Despite this, the strategy any algorithm used in the project have been successful in delivering impressive results, as we have already seen in execution. That's all about connect-4 game implementing using min-max algorithm in AI. Thank you for giving this opportunity.